Hello, my people. Let's go ahead and get started again. This problem right here is sigma k is equal to 1 to infinity of x to the k over a natural log of k plus 1. Let's go ahead and set up the ratio test, and we'll use n instead of k since I wrote n. Well, I'll tell you what, let's just turn it into k. And we have our a sub k plus 1 divided by, or multiplied by, the reciprocal of a sub k, right? And that means that this one cancels out with all but one of those x's, and the natural logs can be stacked to sort of show how they're going to behave in this limit. Natural log of k plus 1, natural log of k plus 2 times x. And then those natural logs are going to get closer and closer and closer and closer and closer and closer and closer together. So as k increases without bound, and therefore that ratio is going to get insanely close to 1. So that becomes x. And when is x, absolute value of x, less than 1? Well, we've done this a couple times before, so we know that it's negative 1 to 1. Now we need to check the endpoints. When x is equal to negative 1, I'm going to get negative 1 to the k over natural log of k plus 1. We've seen this before. This is by alternating. That denominator is going to increase, and therefore each successive term is going to be smaller than the preceding term, and the value is ultimately going to go to 0. That means that by alternating series test, this is convergent. Okay. Now, when x is equal to 1, we don't have a convergent series because we get 1 to the k over natural log of k plus 1. And just like previous problems, we can compare that to a p-series either by direct comparison or limit comparison, and recognize the fact that if the harmonic series is divergent, and this is even less aggressive than just straight up k, then this of course is going to be divergent. That means that our interval is going to include negative 1, so negative 1 less than or equal to x, but it is not going to include 1. Our radius, of course, is just going to be 1, and therein, that is our answer. Okay, next one. Let's just keep on going. Find the radius and convergent for the following power series. Now, let's go ahead. This, again, looks like a ratio test because not everything is raised to the power. Let's do the limit as k approaches infinity. We're going to exclude the negative 1 because that's the whole point of the absolute value. We recognize, of course, that this is centered at 2 and not at 0. So we have x minus 2 to the k plus 1. This is k plus 1 plus 1 becomes k plus 2, and then we'll multiply it by the reciprocal of a sub k. Again, this cancels out with all but one of the x minus 2's here. I'm going to go ahead and stack those expressions in terms of k so we can see them a little bit better. K plus 1 over k plus 2. Now as k goes off to infinity, that's obviously going to go to 1, and what I'm left with is x minus 2. So I have the absolute value of x minus 2, and we recognize the fact that that has to be less than 1 for the power series to be convergent. What that means is when I split it into a 3-part inequality and solve, we notice that x needs to be between 1 and 3. Now, we need to, of course, check the endpoints. So let's go ahead and check at x is equal to 1. When x is equal to 1, negative 1 to the k, but I also get another negative 1 to the k over k plus 1. So that actually, the negative 1's are going to cancel out, and I'm going to get 1 over k plus 1. Which of course is basically, not basically, because it does start at 0. It is the harmonic, right? Because it starts with 1 and goes 1/2 plus 1/3 plus 1/4. It is the harmonic. We know that it's the harmonic, and therefore we know that it is that it is divergent. Okay. So when x is equal to 3, we can see the fact that k is equal to 0 to infinity. We have negative 1 to the k. And up here, 3 minus 2 is just going to give us 1 to the k, or just 1. Now, this winds up being alternating harmonic. Well, alternating harmonic is convergent, right? And we've talked about that, and I've even shown you sort of that visual proof of it. So if 3 is convergent, 1 is divergent, we know that the interval is going to be 1 to 3, but the 1 is going to be inclusive. And we know that our radius, of course, again, is just 1. Alrighty, let's go ahead and take a look at this one. Find the radius and interval of convergence of the following power series. Now, we're not seeing a whole lot of factorials. Those will enter in more and more as we start dealing with particular power series and following sections. Well, let's go ahead and get to this one. We have the limit as n approaches infinity. Sorry, old habits. I'm picking these obviously from a book that loves to deal in k. So we'll call it x plus 1 to the n plus 1 over n plus 1 factorial. I'm just going to go ahead and change everything into n instead of k, just because I started off that way. We recognize also that this does not center at 0. It centers at negative 1. Now, again, when we cancel, all of these cancel with all but one of those. All of this cancels with all but the n plus 1. And basically we get the limit as n goes to infinity of 1 over n plus 1 times x plus 1. The reason that I put it this way is so that the x plus 1 doesn't distract us. As n goes to infinity, this bad boy goes to what? Well, this goes to 0, okay? And it doesn't matter what this is right here. 0 times x plus 1 is just 0. Now, this is a numerical answer. It is always true. So if it's always true, it's always convergent, and it doesn't matter what value of x it is, which is another way of saying negative infinity to infinity, and our radius is also infinite. So our interval is the whole set of real numbers, and our radius is infinite. Okay. Alrighty, let's go ahead and let's do another one. Now, it says find the radius and the interval of convergence for the following power series. Again, this doesn't look like root test. This is ratio test because, the only thing that's raised to the k is that bad boy up there. So we'll say the limit as k goes to infinity of x plus 1 to the k plus 1. K becomes k plus 1. K plus 1 becomes k plus 2. K plus 2 becomes k plus 3. And we have k, k plus 1, and k plus 2, all of that over x plus 1 to the k. K plus 1, k plus 1, k plus 2, k plus 2, x plus, all of this cancels with all but one of that. And let's go ahead and let's rewrite it where we can sort of stack things and see it a little bit easier. Sort of clean it up. You don't have to, but I like to. Okay, now as k goes to infinity, this obviously goes to 1. And so what we have here is x plus 1 less than 1. Well, again, it's nice that it's not centered at 1. Sometimes it gets a little boring when all of the radius of convergence, or almost all of them, is equal to 1. But we get negative 2 to 0. And now we need to check both endpoints when x is equal to negative 2 and when x is equal to 0. So sigma k is equal to 1 to infinity. When x is equal to negative 2, that becomes negative 1 to the k over k, k plus 1, k plus 2. that is obviously going to be divergent, largely because this series is absolutely convergent, as we can see when we pop on over here to this other one, k is equal to 1 to infinity of 1 to the k, k plus 1, k plus 2, and we can do it by comparison to p series. That's going to be k cubed as a leading coefficient in the denominator. Once you expand that out, this is definitely convergent. So our radius is 1. Our interval is going to be -2, non-inclusive, but inclusive of 0. And yay, there we go. Now this next one is going to be one of those rare cases when it actually is best to use the root test. And we can pretty much tell the root test problems by the fact that everything, the whole of the a sub n, or in this case the a sub k, is going to be raised to the k power. Because this actually can be rewritten like this: x over k plus 2 squared, all of that to the k, which means that the limit as k goes to infinity of the kth root of this is just going to be the limit as k goes to infinity of x over k plus 2 squared. Now, again, we don't have any cancellation on this one. The k plus 2 would go to infinity. K plus 2 squared is just going to go to infinity faster, and that's going to make that whole expression go to 0 as k goes to infinity. That, of course, is always, not less than 1, is always less than 1. So that's always true. And remember, when it is always true, we have a radius that is infinite and an interval that is negative infinity to infinity. And so it's just a smattering of examples of the power series problems. We did a few in class. We'll do a few more. You have a couple of homework assignments that will walk you through some of those examples as well. But as always, if you have any questions, please do shoot me an email. Bye.